Okay, so this is an example of a kappa calculation where we're looking at the agreement between two raters, two observers. So let's look at this example from the Gordis 7th edition textbook in epidemiology. Two physicians are asked to classify 100 chest x-rays. This makes it really easy because 100 you can get a percent. Chest x-rays as abnormal or normal independently. The comparison of their classification is shown in the table below. So you have these two raters, physician one and physician two, and you can see physician one rated 60 as abnormal, 40 as normal. Physician two had 50 normal, 50 abnormal. Really easy to do here. So really what we want to do is calculate the kappa. It's broken down here based on just on different parts of the calculation, and then you're asked to rate it as excellent, intermediate to good, or poor. Okay, so let's go ahead and do this. I'm just going to use just here you go. Just the work that I did. I just did this right now. I'm trying to make this short video before class. So here's a Kappa statistic. It's the percent in this case, percent because we're at 100% of observed agreement minus the percent expected agreement, divided 1 minus the percent expected agreement. So expected is what's expected by chance alone. What's above and beyond that is that area in which we can play to improve our agreement, right? So that's what we're trying to do, improve our agreement above the expected. So that's why we subtract from 1. To calculate our expected agreement, we take the probability of, in this case, it says normal, abnormal, but I'll just say positive and negative, positive, normal, negative. Uh, you could do it either way, but just for sake of this example, positive is normal and negative is abnormal. In medicine, usually negative is normal and positive is abnormal, but let's just play around with me here for a second. So you want the probability that they both agree on the positives or they agree on the negatives. So that should invoke the idea of the addition rule and the multiplication rule. This would be the addition rule because we have an or scenario and scenario is a multiplication rule. So let's calculate the percent observed agreement. So if we go back to our table here, they agreed here on 40, right? Because here's the abnormal for physician one and normal for physician two. They cross at the 40. And in term the abnormal, right? In terms of the normal, physician one had 40 and physician two had 50, but they cross at the 30. So these are the two areas in which they agreed, right? They both were saying abnormal here, and they both were saying normal here. So we go back to our our works, we had 40 plus 30, and it's over 100 because there was 100 total. So we get 70, 0.70. Okay, just divide by 100. And in terms of the expected agreement, so I broke this down further into its components because either they both were, so what we want to do is we want to know what the probability of being in a specific cell is. In this case, like what's the probability of being in that cell, right? And then what's the probability of being in that cell? To be in this cell here, you have to have both a determination of abnormal by physician one and, so the and is key here, and a determination of abnormal by physician two, and in probability indicates multiplication. So what's the probability that physician one said the reading was abnormal and physician two said the reading was abnormal? For physician one, that would be 60 out of 100, right? And for physician two, it would be 50 over 100, so 50% and 60%, right? So that and indicates that we're going to multiply those two together, those two probabilities together. But they could also agree on being normal. So for normality, we have physician one saw 40 out of 100 normal, and physician two saw 50 out of 100 normal. So we're going to multiply those two together because they both meet here. So this is the cell where both physician one and physician two thought that readings were normal. So they could either agree in terms of abnormality or indicates addition, right? And indicates multiplication or indicates addition, or with both being normal. So let's go back to our work here. That's what I did here. So the probability that physician one So the percent of expected agreement is the probability that physician one said that the reading was abnormal, and I use this inverted U here to indicate the intersection, right? And physician two said the reading was abnormal, and I put those in parentheses, or let's say I use the um the symbol here, right? Um, if, or them being I can't remember that word right now. That's what happens when you're old. So, or the union, right? The union of the two, or the probability that physician one says they're normal and physician two says they are normal, right? So you have the intersection or the union. So you have the intersection means multiplication, union means addition. So we're going to go ahead and multiply these two probabilities. So that's 60 divided by 100 for physician one, 50 divided by 100 for physician two. Multiply those two, and then add the product of 40 over 100 times 50 over 100. So that's what we get here. We get 0.3 plus 0.2 is 0.5. So we enter these into the kappa equation. Get 0.7 minus 0.5. So this is the observed agreement minus the expected agreement. 1 minus 0.5. So we've got 0.5 is the extent of the space we have available, right? Above and beyond chance. And we get what? 0.2 divided by 0.5 or 0.4. So the kappa thing, really what you have is 0.4. Below 0.4 is considered poor agreement. And you have like good agreement is somewhere between 0.4 and 0.75 or so, and then above 7.5 you got good agreement. This is 0.4. This is just like right at the edge of good agreement. So it's very not very good, my view. But anyway, that's how you calculate a kappa. Thank you very much. I hope if you have any questions, please ask me, and always subscribe to me and all other YouTube channels that you watch, because that's how we end up being supported for making beautiful videos like this. Thank you.